Welcome back. We will now push a little deeper into Chapter 2 of the Dark Art of Linear Algebra, where we will discuss two fundamental notions in linear algebra, the idea of a basis and the notion of a subspace. And this all builds directly on the last video, which was on span and linear independence, so if that is not fresh in your mind, you might want to review that one. So let's begin with a definition. A set of vectors is called a basis for Rn if every vector in Rn can be expressed as a linear combination of the set's vectors in one and only one way. This should remind you of the discussion we had towards the end of the previous video about clean grids and tangled grids. And the idea was that a clean grid was generated by a set of linearly independent vectors. So I'll write down here, linearly independent vectors generate a clean grid, whereas a tangled grid is generated by a set of linearly dependent vectors. And for the sake of our illustration, let's just assume that all of these vectors live in R2. Now this pair of vectors, v and w, clearly span all of R2, which is pervaded by this nice clean grid. And over here, these three vectors also span all of R2, which is pervaded by this tangled grid that the vectors generate. So the two vector sets both span R2. That means every vector in R2, equivalently every point in R2, can be expressed as a linear combination of v and w. We can reach every point through some linear combination of v and w. And similarly, since these vectors span R2, every vector in R2, every point in R2, can be reached as a linear combination of those three vectors. This point, for example, is, let's see, 2 copies of v plus 1, 2, 3 copies of w. So it is 2v plus 3w, that point, or equivalently that vector. While over here, this point could be reached, let's say, as 1, 2, 3, 4 copies of A plus 1, 2, 3, 4 copies of B. So that point would be 4A plus 4B. And in fact, we didn't need any copies of C. So I'll just put 0C on there to remind us of that. But now here is the crucial distinction. In our first scenario, where we had linearly independent vectors generating a clean grid, the expression of this point as a linear combination of the linearly independent vectors is unique. That's the only way to do it. That's the virtue of the clean grid. That's the virtue of the linearly independent vectors that generate the clean grid. Whereas over here in the second scenario, the representations of points as linear combinations of those three linearly dependent vectors is not unique. Sure, we can say this is 4a plus 4b plus 0c, but we could also get there by, say, taking one c step, then one a step, then two b steps, so that we could represent this point as a plus 2b plus c. This is a different representation of that point, or if you like, again, that vector, than this representation was. They both correspond to the same point, the same vector, but they are different linear combinations of the vectors. In contrast, that can't happen here, where we have a clean grid. This is the only way to get to this point. I mean, you could take some other path like this one, but it amounts to the same thing because you have minus w, 2v's, plus 4w. Well, the minus w and the 4w work out to 3w. So there's no getting around the fact that this is 2v plus 3w and only 2v plus 3w. And that is very useful to have unique representations like that, because now for any point in R2, I can specify a particular unique address, a certain number of copies of V and a certain number of copies of W. If you and I do it separately, we will get the exact same thing. Whereas if you and I try to do that separately over here, we might come up with different representations. So this is much nicer. Anyway, what all this is getting at is that these two vectors, v and w, constitute a basis for R2, because our definition says that a set of vectors is a basis for R2 if every vector in R2 can be expressed as a linear combination of those vectors in one and only one way. So if we have a clean grid, we're in business. If we have a tangled grid, we do not end up with a basis, because this uniqueness fails. And of course, this idea of a basis isn't just for R2, it works for R anything. So in R3, for example, I hat, j hat, and k hat, the unit vectors sticking out on the positive x, y, and z axes, constitute a basis for R3, because any point in R3 can be uniquely expressed as a linear combination of those vectors. In fact, these are the so-called standard basis vectors of R3. They generate a clean grid that pervades all of R3, so they span all of R3, and every point in R3 can not only be represented as a linear combination of those three, but can be represented uniquely as a linear combination of those three. For example, this point right here looks like it is reached by taking 2 I steps, 1, 2, 3 j steps, and 1 k step. So this point is 2 I hat plus 3 j hat plus k hat, and that is the unique representation of that point or of that vector as a linear combination of I, j, and k. And although I, j, and k are the standard basis for R3, they're not the only basis for R3. There are infinitely many different choices of basis for R3. For example, take any 3 linearly independent vectors in R3. They have to be linearly independent, of course, to get that clean grid, and therefore that unique representation. But take any 3 such vectors, column A, B, and C, and you should be able to see by now that these span all of R3, and in fact they fill R3 with parallel epipeds of this sort. You can imagine the grid, a few cells of which I've drawn here, and a point like this one looks like, let's see, there's a B, then 1, 2, 3 copies of C, and then a minus A because we're going in the opposite direction of A. So this point would be minus A plus B plus 3C. Not only can we reach that point as a linear combination of these 3 linearly independent vectors, but because they are linearly independent, this is the only linear combination of those vectors that will get us there. So yes, these 3 vectors would constitute a basis for R3. What if we were to restrict our attention to vectors A and B? They are linearly independent vectors, of course, neither lies in the span of the other, but do they constitute a basis for R3? We know they're linearly independent, so that's a step in the right direction, which means that anything that can be represented as a linear combination of the two of them can only be represented in one way, but they are not a basis for R3 because not every vector in R3 can be reached by them. We have to be able to express every vector in R3 as a linear combination of those vectors. So we need uniqueness, but we also need existence in the first place. So those are not enough. Not only must the vectors be linearly independent, but they have to span the entire space. And when you put those two requirements together, linear independence and spanning the entire space, you can come up with an equivalent definition for a basis, one that you will often see in many linear algebra books. So maybe I should write that down too. Equivalent definition: a set of vectors in Rn is a basis for Rn if the vectors 1 are linearly independent and 2 span all of Rn. So this is another way of saying the same thing that we've said over here, and you should be able to understand why they are equivalent, why they're saying the same thing. The idea is that this condition, that the vectors span all of Rn, is what guarantees that every point in Rn, every vector in Rn, can be expressed in at least one way as a linear combination of the given vectors. And that is part of our definition here. Every vector in Rn can be expressed as a linear combination of the set's vectors. The other condition, that they have to be linearly independent, that is what ensures that that representation is unique in one and only one way. So this is the definition of a basis you are more likely to see in a typical linear algebra book. And it's a perfectly good definition, but if you don't have the intuition behind it, it can make you wonder why such a thing is being defined in the first place. So just bear in mind what it is accomplishing. Those two criteria, linear independence and spanning all of Rn, are what together give us the uniqueness of representations of points as linear combinations of the basis vectors. If the vectors didn't span all of Rn, then some points wouldn't have any representations as linear combinations of the vectors. And if the vectors weren't linearly independent, then points that could be represented as linear combinations would have many representations, not just one. Okay, I think you've got the idea now of what a basis of Rn is. A basis for Rn, intuitively speaking, is some set of vectors that generates a clean grid pervading the entire space, thereby supplying every point in that space with a unique address. And I will have more to say about bases soon, because it is not only all of Rn that can have a basis. We can have a basis for smaller pieces of Rn, which are known as subspaces of Rn. But before we can talk about that, we need to talk about what a subspace of Rn is. So let's do that. Rn, for whatever value of n you like, is the canonical example of a so-called vector space. And a vector space in general is simply any setting in which it is possible to do linear algebra. We can specify exactly what that requires by writing down axioms for a vector space, but we don't need to do that here. That is appropriate for a more abstract approach to linear algebra. But the term vector space is good to know, in part because it will help us make sense of the idea of a subspace. A subspace is simply a part of a vector space that functions as a vector space in and of itself, so that we can concentrate just on the subspace and do linear algebra there without having to think about the larger vector space of which our subspace is just one chunk. A subspace is like a self-contained little world within a vector space, and it's a world in which we can do linear algebra. It is itself a vector space, and it may have its own subspaces. Let me lead you closer to the concept with some examples. R3, or three-dimensional Euclidean space, is surely our most familiar vector space because we live in three-dimensional space. R3 has lots of subspaces. I want to begin by showing you something that is not a subspace. A sphere centered at the origin. Now, the sphere is definitely a chunk of the vector space R3, but it's not a subspace of R3 because we can't do linear algebra simply confined to the sphere. What I mean by that more specifically is that linear algebra is based ultimately on the two vector operations of vector addition and scalar multiplication. Those don't work if I confine myself to this sphere. For example, take a point on the sphere, or if you like, the vector pointing to that point. We're thinking of the two as the same thing, of course. Well, suppose I scale that vector. Maybe I multiply that vector by 2. What happens to it? Well, this vector becomes this vector, twice as long and pointing to some point that is not on the sphere. Well, so much for doing linear algebra on the sphere. Simply scaling a vector on it turns it into something that is no longer on the sphere. That won't do. So this sphere is not a subspace of R3. Well, let's try again. How about a cone in R3 whose tip is at the origin and which opens upward? And you have to imagine this cone is infinite in extent. There's just only so much I can draw on the page, of course. It just goes on up forever. It's a perfectly good chunk of R3, but is it a subspace? Can we do the basic operations of linear algebra there? Can we add and scale vectors? Well, let's think about it. Suppose we have a point on the cone, or equivalently a vector pointing to that point. And suppose we want to scale it by 2, just like we did over here. Do we stay on the cone? Well, yes, we do. We just move further up the cone. Hey, that's encouraging. Or what if I scaled it by 17? Yep, we just travel further up the cone and we'd still be on the cone. Or what if I took some other point and scaled its corresponding vector by 1/2? Well, no problem. That would still be on the cone. Or what if I scaled it by 0? Still no problem. It would just take me right to the tip of the cone. But what if I scaled it by something negative? Like if I scaled it by -1. Ooh, that would put me back here and I would be off the cone. That means this cone is not a subspace. But wait, someone may object. If you've, say, studied conic sections in any serious way, you probably know that we often think of a cone not just as a single cone like that, but as a double cone. Something more like this. The idea is you start with a point and you have a line running through that point and you rotate that line around another line and that sweeps out the entire cone, top and bottom. But anyway, if I have this double cone, or a cone with 2 naps, as they call it in geometry. Will that do the trick? Looks like we've at least staved off one criticism, because if I take this green vector here and scale it by -1, well, we end up with something like this. We get a point that is on the cone. So now it appears that we can take any point we like anywhere on this double cone, scale it by any scalar we like, positive, negative, or 0, and we stay on the double cone. Does that mean the double cone is a vector space? No, it does not. We've cleared one hurdle. We can scale vectors on this thing and stay on that thing, but can we also add them? If you think about it for a little while, you will quickly realize that we cannot. For example, if I add this blue vector on the upper part of the cone to this red vector on the lower part of the cone, like so, we end up at a point that is definitely not on the cone. So we can't do vector addition on this cone and remain on this cone. And so this double cone is also not a subspace of R3. For a chunk of R3 to be a subspace of R3, we have to be able to take linear combinations of vectors on it. So we have to be able to add vectors and scale vectors on it and still remain on it. Well, now that I've shown you some examples of subsets that are not subspaces, maybe we should write down a proper definition of a subspace, and then we will start looking at some actual examples. Definition: a subspace of a vector space, such as Rn, is a subset of the vector space that is closed, and I'll specify exactly what this means in a moment, under scalar multiplication and vector addition. This notion of closure is exactly what we were talking about down here. To be closed under scalar multiplication means that if you scale a vector within that set, it stays in that set. So for example, this double cone is closed under scalar multiplication. On the other hand, the double cone is not closed under vector addition, because we can take two vectors in that set and add them together, and we end up at a point that is no longer in that set. It's not closed under vector addition. And similarly, in our first example, we saw that this sphere is not closed under scalar multiplication. And it should be easy to see, I'll leave it to you, that it is not closed under vector addition either. So a subspace must be closed under both operations. So now let's look for some positive examples of subspaces. And to make our search a little easier, let's leave R3 for the moment and drop down to R2. Let's begin with the smallest subspace in the world. A silly subspace, but an important one for all that. Suppose we just look at the origin. Well, that's only one point, or one vector, namely the 0 vector. I claim that the origin all by itself constitutes a subspace. All we have to check is it closed under scalar multiplication? And is it closed under vector addition? Well, let's see. Suppose we scale the 0 vector. Well, it doesn't matter what we scale it by. 42 times the 0 vector is the 0 vector. Minus 212 times the 0 vector is the 0 vector. So you can scale this thing by anything you want. You still end up at that same point. So yes, it's definitely closed under scalar multiplication. Is it closed under vector addition? Well, take two vectors from this set. You don't have any choice. You're taking 0 and 0. You add them together, and what do you get? Well, you get the 0 vector, which is still in the set. So yes, it's closed under vector addition as well. That means that the origin alone is a subspace. It's sometimes called the trivial subspace for obvious reasons. Okay, so there's our 0-dimensional subspace. Can we come up with something a little more interesting? Well, you might say, is there anything special about the origin? What if I just took some other point? Could I say that this point alone is a subspace? No, of course not. It's not closed under scalar multiplication. If we took that vector and scaled it by 2, we would get to a point that is not that original point. So this point all by itself certainly is not a subspace. The only isolated point that is a subspace is the origin itself. And more interestingly, and this is why the trivial subspace is somewhat interesting, every subspace that can possibly exist must contain the origin. Because let's just say this other point that's not the origin is in some subspace. Now, I don't know what the subspace is going to look like, but let's just say we know this point happens to be in that subspace. Well, since this point is in the subspace, all scalar multiples of this vector lie in the subspace. In particular, scaling that vector by 0 gives you a point in the subspace, which is the origin. So that means the origin itself is a subspace, and if there are any points other than the origin, then the origin still has to be in the subspace. So there's no getting away from the origin. Every subspace contains the origin. But anyway, let's get back to what I was saying before. We're on the hunt for subspaces of R2. We know the origin has to be in there. Suppose some other point that is not the origin is in there. Okay, so now I have a subspace that contains the origin and this second point. Well, we said before that if it contains this point that is not the origin, it contains the vector pointing to it, which means it contains all scalar multiples of that vector. But all scalar multiples of that vector, the span of that one vector, gives us an entire line through the origin. Hey, so this is pretty interesting already. Every subspace contains the origin, and if it contains any point that's not on the origin, it contains the entire line through that point and the origin. So now we know that if we just have a sprinkling of points somewhere, that can't be a subspace. Okay, so we've got this entire line through the origin. Is that line itself a subspace? Well, let's think about it. If I take any point on the line, or equivalently any vector on the line, and scale it, do I stay on the line? Certainly I do. Like this one, if I scale it by a positive number, I end up with a vector that's pointing this direction. If I scale it by a negative number, I end up with a vector pointing in this direction. And if I scale it by 0, well, I end up at the origin. So this line is definitely closed under scalar multiplication. Is it closed under vector addition? Absolutely. Just think about how vectors add. If I take two vectors on that line and add them, well, we add tip to tail, so we end up with a vector on the line. And of course, it doesn't matter if my vectors point in opposite directions initially, as they did here, or in the same direction initially, as these two do. When you add them, you just get another vector on that line. So this line through the origin is closed under both scalar multiplication and vector addition. That means it is a subspace of R2. Hooray, we found one! And there's nothing particularly special about this line. Any other line through the origin is a subspace of R2. For the exact same reasons. Hey, someone might ask, does it have to go through the origin? What about a line that doesn't go through the origin? Is that a subspace? No, it can't be a subspace. As we said already, every subspace has to contain the origin. Don't just remember that statement, remember why it is so. If I took any point on this line not passing through the origin, like this one, I can immediately see that this line not passing through the origin is not closed under scalar multiplication. That point corresponds to a vector that looks like this. Scale it by anything you like, and you get something that's not on the line. So that one is out. All right, let's rest for a second and take stock of what we've learned. Subspaces of R2. Well, we found the origin, or the set consisting just of the zero vector, and lines through the origin. Let's continue our systematic hunt to see what other subspaces of R2 there might be. Well, we said any subspace has to contain the origin, because subspaces are necessarily closed under scalar multiplication. And we said that if a subspace contains any point besides the origin, then it has to contain the entire line through the origin and through that point. Again, due to the closure under scalar multiplication. But suppose our subspace contains more than just that line. Then it would have to contain some other point that doesn't lie on the line, like this one, or equivalently this vector. Oh, but in that case, our subspace would contain two linearly independent vectors. And since the subspace is closed under both scalar multiplication and vector addition, meaning that it is closed under all linear combinations of vectors therein, then any vector we can reach with linear combinations of these two linear independent vectors would also be in the subspace. In other words, a subspace containing this line and this one extra vector would contain the entire span of those two linearly independent vectors. And the span of those vectors, as we know from the previous video, would be all of R2, because linearly independent vectors generate a clean grid pervading the entire plane. So that's it. Our subspaces can either be the origin, or once there's a point other than the origin, a line through the origin, or once we have a line and a point not on that line, all of R2. And you might object, well, all of R2 isn't really a subspace, is it? I mean, it's the whole space. That's true, but we still consider it a subspace, even though it is the whole space. But we can see what's going on here now. Our subspaces of R2 contain the origin, which is a zero-dimensional subspace, lines through the origin, which are one-dimensional subspaces of the ambient two-dimensional space, and all of R2, which is, of course, the one and only two-dimensional subspace of the two-dimensional ambient space. Now let's take a look at subspaces of R3, and we can analyze this the same way. Again, the origin remains a subspace for the same reason it was in R2, and for the same reason it will be in R4 or R5 or R20 million. Lines through the origin, such as this one, are subspaces of R3 for the same reason. Scale any vector on such a line, and you get something on the line. Add any two vectors on such a line, and you get something on that line. So yep, lines through the origin are still subspaces of R3, but now it's a little more interesting, because if we take some point, that is some vector that does not lie on that line, but yet which is in a subspace along with that line, well, we still have the same scenario that we had before, where we know that if we take any vector that lies on the line, it and our new vector are linearly independent and thus span an entire plane, a plane that of course contains the origin. We know that that entire plane will lie in the subspace, but now that entire plane is not the totality of the space as it was when we were working in R2. It's just one plane in R3 passing through the origin. And if we were to take that entire plane through the origin, would it constitute a subspace of R3? It would. Clearly, if you scale any vector in such a plane, you end up with a vector in that plane. And if you add any two vectors in that plane, you end up with a vector in that plane. So we have a new type of subspace. Planes through the origin. These are two-dimensional subspaces of the ambient three-dimensional space. And of course, there was nothing special about the one I drew. Any plane through the origin is a two-dimensional subspace of R3. And the plane does have to pass through the origin. If it doesn't pass through the origin, it is not a subspace for the reasons we have detailed several times now, having to do with scalar multiplication. Okay, so suppose I have a subspace of R3 that contains a plane through the origin, but is not just a plane through the origin. It also contains at least some point, like this one, that does not lie on that plane. What can we say about our subspace then? Well, it will contain this vector as well, which is sticking out of this plane, and the three vectors I've drawn will all be linearly independent. That means they are going to generate a grid that pervades all of R3. In other words, those three vectors will span all of R3. And since those three vectors are presumed to be in a subspace, and subspaces are closed under linear combinations, that means every point in their span, in other words, every point in R3 will lie in the subspace, which means that as soon as the subspace goes beyond a plane through the origin, it becomes all of R3, our one and only three-dimensional subspace of R3. Do you see where this is all headed? I'll bet you do. What are the subspaces of R4? Ah, R4. I can't picture it. Doesn't matter. You don't need to picture it. Look, of course we know the origin is a subspace of R4. But how do we know? Because it satisfies the definition. You scale the zero vector, you get the zero vector. You add the zero vector to itself, you get the zero vector. Therefore, it is closed under linear combinations, which means it's a subspace. Lines through the origin are the only one-dimensional subspaces of R4. For precisely the same reason, they were subspaces of R2 and R3, even if you can't picture them. I mean, you kind of can picture them because, and this is the whole importance of a subspace, all the action takes place in one dimension, and you can picture one dimension. I mean, whatever R4 looks like, it has an origin. And if you have a subspace that contains a point that is not the origin, well, the vector pointing to that point can be scaled by any scalar, positive, negative, or zero, which generates a line through R4, through the origin of R4. So the whole line has to be contained in the subspace. And it is a subspace. It's obviously closed under scalar multiplication, as we said, and vector addition, because you add two vectors on the same line, and you get another vector on the same line. Planes through the origin of R4 are also subspaces of R4. They are the only two-dimensional subspaces of R4. And again, even though you can't picture R4, you can picture a two-dimensional plane. It's just a two-dimensional plane, whatever ambient space it's sitting in. We've got some line through R4. Never mind how spacious it is around that line. We've got some other point in that mysterious ambient space. There's a vector, a one-dimensional creature, that points to that point from the origin. And now we've got two vectors that are linearly independent. They span a ordinary two-dimensional plane. Sure, it's in the mysterious R4, but it's a two-dimensional plane. Works the same as when this was all in R3 or even in R2. But in this simple case of R2, that plane was all of R2. In the case of R3, that plane split R3 into two halves. Everything in R3 was on one side of the plane or on the other side of the plane. In R4, the situation is a lot trickier. A two-dimensional plane in R4 actually does not divide all of R4 into two regions. You can see this by thinking analogously. A line in R2 splits R2 into two separate regions. It divides it into two separate halves. Everything is on one side or the other. But a line in R3 doesn't do that at all. You can get all the way around the line without ever crossing it. Well, something similar happens with two-dimensional planes in R4. Anyway, the details of that are not important for us right now. It's just something fun to think about. But anyway, planes through the origin, ordinary two-dimensional planes, are subspaces of R4. So if I have some plane through the origin in R4, and it is part of some subspace, but the subspace contains more than that plane. It contains some point and therefore some vector lying outside of that plane. Well, then I can pick any two linearly independent vectors in the plane, and I know that those three vectors, being linearly independent, will generate a clean grid and therefore span an entire three-dimensional space. But it won't be, as it was in the case of R3, the entirety of the space. It will just be one three-dimensional space in R4. In other words, it will be a three-dimensional hyperplane in R4. And of course, it will pass through the origin. Those are our three-dimensional subspaces of R4. Now, I can't possibly draw a three-dimensional hyperplane for you. I mean, I'm trying to simulate something in three dimensions on this two-dimensional surface, the tablet that I'm drawing on, the computer screen you're watching this on. We're good enough at the three-dimensional play acting that you can imagine those three vectors generating a clean grid of parallel epipeds like that one that fill up all of a three-dimensional space. That three-dimensional space is a three-dimensional hyperplane. What does it look like? What does it look like? I don't know. I guess it probably looks like the space we inhabit. For all I know, our world, which appears to be three-dimensional, may well be one hyperplane, one three-dimensional hyperplane in a four-dimensional universe. Okay? So what if we somehow, and now I can't draw it at all, we have to imagine this three-dimensional hyperplane, which somehow resembles the entirety of the three-dimensional space we inhabit. It's a flat, infinite, unbounded three-dimensional space, just like a plane is a flat, infinite, unbounded two-dimensional space, or a line is a flat, unbounded, infinite, one-dimensional space. Anyway, we've got this three-dimensional version, a three-dimensional hyperplane, that exists in an ambient four-dimensional space. Whatever. It's out there, however we want to represent it. We've got some subspace that contains not only it, but at least one other point in the four-dimensional space that does not lie in the three-dimensional hyperplane. So we've got some vector sticking up from the origin, which we know is in our subspace because it's in every subspace, to that point. And we can find, because we're in a three-dimensional hyperplane, three linearly independent vectors in that hyperplane. And you might say, wait, that looks like they're linearly dependent. I know it looks like that. I'm drawing it in a two-dimensional space. There's nothing I can do about it. We have to use our imaginations here. These three linearly independent vectors span the entirety of the hyperplane. Put them together with this fourth vector, and we now have four linearly independent vectors in a four-dimensional space. Well, they are going to span the entirety of that four-dimensional space. They generate a clean grid that pervades all of R4. So this subspace that contains that three-dimensional hyperplane and even one more point outside of it has to be all of R4. There's nothing in between. So the last subspace on our list would be all of R4. And that is our complete list of subspaces of R4. And I'll bet you could come up with the subspaces of R5. Yep, it would be the origin. Lines through the origin would be the one-dimensional subspaces. Planes through the origin would be the two-dimensional subspaces. Three-dimensional hyperplanes through the origin would be the three-dimensional subspaces. Well, not all of R4. Next, we would have four-dimensional hyperplanes through the origin, and finally all of R5. And in fact, if we were to look at subspaces of not R5 but Rn, we get the origin, lines through the origin, planes through the origin, three-dimensional hyperplanes through the origin, four-dimensional hyperplanes for the origin. I'm assuming n is a large number here, etc., 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 all the way to n-1-dimensional hyperplanes through the origin, and finally, all of Rn. In short, the subspaces of Rn are the flat, infinite, unbounded objects therein, well, and the origin. Now, let's jump back to R3. R3 is a perfectly good vector space, and so is this plane through the origin that I've just drawn. It is a subspace of R3. That means it's a vector space in its own right. We can do linear algebra in that plane alone. That means we can talk about a basis for that subspace, which is a set of linearly independent vectors that span the subspace. So in my picture here, I've just drawn two linearly independent vectors in this plane. They span the entire plane, that is, they span the entire subspace, so they are a basis for the subspace. They generate a clean grid that fills the whole subspace up and which endows every point in the subspace with a unique address, a certain number of copies of the blue vector plus a certain number of copies of the red vector. So it's not just Rn that can have a basis. A subspace admits a basis as well. And as I briefly remarked earlier, subspaces themselves can have subspaces. For example, in the picture I've drawn, this plane through the origin, I can pick out a line through the origin that lies on that plane. Well, that is a one-dimensional subspace of all of R3, but I could also think of it as a one-dimensional subspace of this two-dimensional subspace, the plane, which itself is a subspace of R3. And of course, contained in all of them is the origin itself, the tiniest subspace in the world. Okay, well, we had a little talk about hyperplanes, and I want to say a bit more about them in the next video, because even though they're not the sort of thing you can readily visualize, we will be working with them a lot. So we will be talking about how to cope with them algebraically. Again, it's the interplay between the geometry and the algebra that is so powerful here. I can't see them, but I can describe them algebraically, and we'll think of two different ways to describe them, both with ordinary Cartesian equations, and just as importantly, we will come up with parametric representations of hyperplanes. But that is in the next video. That is all I have to say for this one. So farewell, have a nice day, nice evening, nice whatever time it is you're watching this. Goodbye.